In Chapter 8, we're going to talk about the behavior of gases in chemical reactions. And while gas phase chemical reactions can still be described using all the tools you've learned before, like balanced chemical equations, the way we measure the amount of gases and convert and figure out number of moles of gas participating in a gas phase chemical reaction is quite a bit different than the way we deal with solids or liquids and solutions. In solids or liquids or solutions, the most straightforward way is always to go either use the mass of the chemical and its molar mass to figure out how many moles are participating, or use the concentration of a solution and the volume you used to figure out how many moles of a chemicals are participating. Gases are a much more dispersed solution or dispersed mixture than an aqueous phase solution. The amount of gas that it takes to fill your entire room you're sitting in now boils down to a relatively small amount of particles and a relatively low mass. Gases are so dispersed that it's not really convenient to talk about the mass of a gas and relate it to the number of moles that are participating in chemical reactions. Instead, to figure out how much gas is going to participate in a chemical reaction, the amount of gas is related to observable quantities like pressure and volume instead of mass. And through the pressure and volume of the gas, we can figure out how many moles of gas there are to participate in a chemical reaction. So a large part of this chapter is going to involve teaching you a new set of tools to decide how much gas is present in a chemical reaction mixture and how you connect the pressure or the volume of the gas to the number of moles of gas. And then we'll use molar mass, balanced chemical reaction, all the tools we've used before to figure out limiting reactant problems and basic stoichiometry in gas phase chemical reactions. But first, we need a new tool set, and we need to talk about how we describe the amount of a gas through observed quantities like pressure or volume, and then relate that to the number of moles. And while we usually think about chemistry as happening in a lab, in beakers and test tubes, and that's kind of our experience, some of the most important industrial chemistry and the chemistry that has the biggest impact on the well-being or does the most harm to different parts of human civilization actually occurs in the gas phase. It involves chemical reactions where the products are dispersed into the atmosphere, explosions, combustion reactions. The combustion of natural gas is essential to understand its potential as a fuel source. Gas phase chemical pollutants can be released in the atmosphere and have a huge impact on the population right where they're released, and can also be dispersed more easily all around the world, impacting people who live far away from the pollution source. In the thermochemistry chapter, we also introduced you to the chemical reaction that describes the Haber-Bosch process, the process by which atmospheric nitrogen, N2, is reacted with 3 moles of dihydrogen to give 2 moles of ammonia. All this happens in the gas phase over a solid catalyst, and this is the chemical reaction by which we take nitrogen out of the atmosphere and use it to make fertilizer. So this chemical reaction is maybe the most important industrial chemical reaction in the world because it's the chemical reaction that allows us to make fertilizer and make arid land farmable and feed a much wider segment of the human population than we could if we didn't have access to effective fertilizers. The reason we talk about gases in this chapter as though their chemistry is fundamentally different from solids or liquids is because gases are the most dispersed form of everyday matter. Probably in a previous science course, you've been exposed to the idea that if you look at the molecules or the atoms, what we call the particles that make up the different phases of matter, in most solids, the particles are locked tightly into place, they're rigid, they can't shift past each other. And as a result, a solid is not compressible. It has a specific shape that generally doesn't change. In a liquid, there's no chemical change between a solid and a liquid phase of any chemical. But instead, it's the intermolecular attractions, the interparticle attractions that are disrupted. And in most liquids, which flow out and can be held in a container but don't keep a rigid shape, The particles that make up the liquids are looser. They're free to move past each other. They vibrate more. They're more constantly in motion. If you put more energy into the system, the liquid becomes a gas as these intermolecular forces are further overcome. And now a gas is made up of many dispersed particles that are on average very far away from each other, and they expand to fill their space. As a result, when we're dealing with gases in a chemical reaction, how the particles react inside the context of the chemical reaction is not really different than how a solid or a liquid participates in a chemical reaction. But what is different is that for most gases, the particles are so far apart and the samples occupy such a large volume, it's not convenient to figure out how many moles of a chemical are in a gas sample based on a weight, because you can rarely take your gas sample and put it on a balance and figure out how much it weighs, unless you've been very careful in how you collect it. And you collect it in a compressed atmosphere vial that shrinks its volume down very much. Instead, gases expand and fill their surroundings. So in general, you can think of a mole of gas is going to occupy a volume of space of around 24 liters at room temperature. And so you think of a mole of gas would take up kind of round about an entire bedroom at minimum at room temperature. And so there's no easy way to weigh that out. Instead, when we talk about how much gas is participating in a chemical reaction, then we have to talk about it in terms of other measurable properties usually rather than its mass. And in general, we talk about the amount of gas in terms of either number of moles, which is abbreviated lowercase n, the pressure the gas is exerting, P, or the volume of space the gas occupies, V. Pressure and volume can be related to the amount of a gas phase sample in moles using some simple gas laws that are combined into one single law that describes the behavior of most gases very well at room temperature and 1 atmosphere of pressure, which we call the ideal gas law. So the early part of this chapter is going to be very much a discussion of what is pressure, what is the volume of space that a gas occupies, and how can we use a pressure or a volume measurement to figure out how many moles of a gas are in a gas sample. And it's worth pointing out that initially in this chapter, we're going to deal purely with what we call ideal gases. Ideal gases describe gas samples where we make some simple mathematical simplifying assumptions to make the properties of the gas easier to calculate without so many detailed mathematical correction factors. And we teach you ideal gas behavior first, not only because ideal gases are simpler to visualize and treat with mathematics, but if you're talking about a gas at room temperature and typical atmospheric pressure, the gas behaves very nearly ideally. It's only as the temperature of the gas sample decreases to the point where it starts to be near its condensation temperature, or the pressure on the sample begins to really compress the gas, it's only as a gas is close to transitioning back into a liquid that its behavior significantly deviates from this ideal picture. And in general, we can talk about the behavior of a gas very accurately if we treat it as an ideal gas and make the following assumptions. So the first thing you need to recognize when talking about a gas sample, we immediately go back to this kind of cartoon particle idea of what the phases are look like. Solids are ordered balls that are locked into place. Liquids are kind of flowy blue balls that are free to slide past each other. In the gas phase, the balls, the particles, are in constant motion. They've got a lot of kinetic energy. They're pinging off each other. They're bouncing off the walls of their container, and they're constantly colliding with each other. And so this makes gases fundamentally very different in their behavior from solids or liquids. And so in order to connect measurable properties like pressure and volume most easily to the number of moles in a gas sample, we make the following mathematical assumptions that make our lives a little easier in terms of relating pressure and volume to number of moles. So these are the set of assumptions that describe what we call an ideal gas sample, which is the way we're going to treat gases right up till the end of this chapter. So we say gas is ideal if a gas consists of tiny particles moving at random. This isn't an assumption. That is fundamentally what a gas is. Tiny particles, where particles are either molecules or atoms, whatever the smallest representative chemical unit of the gas is a particle in constant random motion. Then we start to make assumptions. Point number 2, we assume for an ideal gas that the volume of the particles is infinitesimally small. And infinitesimally is a mathematical word that doesn't just mean really small, but it means there's a mathematical approximation where inside the gas sample, we can assume that the volume of the gas particles themselves is essentially zero compared to the volume of space that the whole sample occupies. So what we're saying is, for an ideal gas, we assume that the volume of the gas sample that's actually occupied by the particles is so small compared to the volume of their container that we can treat that volume as if it were zero. And that's an important simplifying assumption. Thirdly, we assume no attractive or repulsive forces exist between the particles, and so their collisions become perfectly elastic. And this is another important simplifying assumption. It's not really true. This is an assumption of the ideal gas law that definitely starts to fall down as you look at more situations of real gas behavior, because there definitely are intermolecular forces that can still act between gas particles when they collide. But in general, the gas particles are so far away from each other most of the time that we can simplify our math by treating those attractive or repulsive forces like they don't exist, because the particles are generally too far apart for those attractive or repulsive forces to make a difference. And if we assume that the collisions between the particles become perfectly elastic, which further simplifies our math. Point number 5, which is again not an assumption but is a truism, the average kinetic energy of the particles is proportional to the temperature in Kelvin. And so the biggest thing I want to bring up here, which I'll bring up again and again until you're very, very sick of it, is that when we're dealing with gas phase samples and we make predictions about their behavior at a specific temperature, we need to deal with the temperature in Kelvin. That turns out to be really important for reasons that we'll talk about later on when we come to them. All right, so in this chapter, the main goal is we're going to show you how to use the ideal gas law to make accurate predictions about the behavior of gas phase chemical reactions. We're going to talk about pressure and how we quantify pressure. We're going to talk about the relationship of a gas sample between its pressure, volume, temperature, and number of moles. And we're going to unify all these measurable properties using one single law, which we call the ideal gas law. The pressure of a gas times the volume of the gas equals the number of moles times a constant times the temperature of the sample. We call the ideal gas equation PIV-NERT, and it's a one-stop shop that allows you to calculate the number of moles in a gas sample if you know the pressure, the volume, and the temperature of the sample. Ultimately, we're going to use the ideal gas law to show you how to calculate the number of moles in a gas sample, and then we'll talk about how we can use the ideal gas law in conjunction with the chemical tools that we've already picked up, interpreting balanced chemical equations, using molar mass, using density to solve some basic problems related to gas phase chemical behavior. Then we'll segue out of the chapter talking a little bit about how gases diffuse and talking about deviations between ideal and real gas behaviors. Your assigned reading for this chapter is all of chapter 8, so that's sections 8.1 through 8.6. I've highlighted some of the most important vocab that you're going to need to get some mastery over on this slide here. And with that, I'll leave the introduction and I'll see you back here in just a few minutes to talk about the pressure of gases.